Okay, hello and welcome back to Chemistry Talk. Today we'll be discussing colligative properties, one of my favorite topics in chemistry. This goes along with our solutions unit because it has to do a lot with concentration expressions, one in particular, but I'll get to that. And today we're focusing on the colligative properties of non-electrolytes, so molecular compounds. Electrolytes are a little bit different, and I'll explain why, but this video will focus on the colligative properties of molecular compounds. So there's three colligative properties: vapor pressure, boiling point elevation, and freezing point depression. Vapor pressure is usually symbolized as Vp, boiling point elevation is BP, and freezing point depression is FP. Now, a lot of different ways to um, symbolize them, but these are the three main colligative properties, and colligative properties depend on the number of solute particles in the solution. That's because to calculate colligative properties, you need the molality. Now, molality is a concentration expression. I have a video on it, but you are going to need to be able to use molality, be comfortable with it. But the formula for molality is moles of solute over kilograms of solvent. So the reason why colligative properties depend on how many solute particles there are. You see, it depends on the solute particles. That's because to find colligative properties, you need to have moles of solute, and depending on how, if this number is big or small, you can calculate that. So that's why the colligative properties depend on the number of moles of solute. So the first one I'll start with is boiling point elevation. The normal boiling point of a liquid is a certain temperature, and the vapor pressure of that liquid is equal to the pressure acting on the liquid externally. And I'll get into vapor pressure in a few minutes. But in a solution of a non-volatile solution, so a solution that's going to behave nicely, in a volatile solvent, the vapor pressure is lowered. So if the vapor pressure of the volatile solvent needs to reach the external pressure, you need to supply more heat. And in this concept, you raise the boiling point of the solution. So that's why it's called boiling point elevation. Now, to get the boiling point elevation, you have the change in boiling point. So the initial boiling point minus the final boiling point, that's your change in boiling point elevation, equals the molality of the solution times the Kb. Kb is a constant. It's the boiling point elevation constant for whatever solvent you're using, and you'll always be given that. Similarly, the freezing point depression has a similar formula. It is delta TF, so the change in freezing point depression, also equals the molality of that solution times the Kf, the freezing point depression constant. Now, for a liquid to freeze, the particles have to be attached and condensed into a solid. And in a solution where the solute's non-volatile, the non-volatile solute prevents the particles in that solution from being tied down. So that means to form a solid, you need to lower the temperature, and that results in a lower freezing point. And that's what the freezing point depression is. Okay, so the more interesting one, and the one that you get a lot more conceptual questions about, is vapor pressure. Now, what is vapor pressure? Vapor pressure is when a liquid evaporates. So let's say I have some water in here, some water. When a liquid evaporates, there's pressure that is exerted on the liquid from the top, and there's pressure that's exerted on the meniscus of the liquid, or the top of the liquid, by the solution. And now what's happening is you have these little particles of the solution that are exerting a lot of pressure on the surface. Now, the vapor pressure is influenced by the strength of the solvent's particles, because if the strength of the particles are stronger, then less molecules at the surface are going to be able to escape, and that's going to result in a lower vapor pressure. But if you have a compound with weaker intermolecular forces, then the molecules are going to be able to escape more quickly, and you're going to get a higher vapor pressure. So intermolecular force strength would mean you have a lower vapor pressure. So higher forces, you have a lower vapor pressure. Weaker forces, you have a higher vapor pressure because it's easier for the molecules to escape. So that's what this is saying right here. Now, if you add a solvent or a solute into this liquid, you're actually also going to lower the vapor pressure, and that's demonstrated here. So here I have pure water. All of the molecules in here are homogeneous, meaning they look the same. And you're getting a relatively rapid rate of a vapor pressure. So here the vapor pressure is relatively high. But here I'm adding a non-volatile solute and I'm disrupting that process. The molecules of water in here want to interact with this new solute that I've added. So the molecules are going to escape at a lower rate. See, there's less molecules escaping here, and that's going to result in a lower vapor pressure. So that's an important concept to understand. If I add a non-volatile solute, you're going to lower the vapor pressure because the solution or the solvent is going to want to interact with those molecules, causing the vapor pressure to go down. So polarity and colligative properties are important because if you're comparing the colligative properties of a bond with the same polarity, the bond that's more massive, meaning it has a higher molecular weight, will have the higher boiling point. Therefore, it would have a lower vapor pressure and a lower freezing point. So the way that these three colligative properties are related is if your boiling point goes up, that means you have a strong compound. It takes a lot of energy to release those bonds, so you have a higher boiling point. Inversely, you have a lower vapor pressure. Because you have a stronger bond, not many molecules are going to escape at the surface. If you have a higher boiling point, you have a lower freezing point because those are related. So the lower the freezing point, the higher the boiling point, the lower the vapor pressure. And this is opposite too. So if you have a low boiling point, it's easy for those molecules to escape. So you're going to have a high vapor pressure, but you're going to have a higher freezing point because the bonds are weaker. So if you want to compare the colligative properties, these three being the colligative properties of bonds, and they have the same polarity, you're just looking at the weight. So let's say
It's 6 o'clock.
let's say I have a hydrogen sulfide. Now this bond is highly polar, just a polar bond because of the Lewis structure. And then let's say I have ethanol I'm comparing it with. And that's also polar. Ethanol is C2H6O. And I want to know which is going to have the higher boiling point, saying that they are both polar. Well, which one is more massive? Hydrogen sulfide is going to be about 34 grams. This is going to be a lot more than that. So ethanol is going to have the higher boiling point because it's more massive. And that's what that idea of polarity. Since they're both polar, I can compare them solely based on weight. If I was looking at a nonpolar bond and a polar bond, the nonpolar bond would have the lower boiling point. So, like I said, the relationship between the colligative properties, the higher the vapor pressure, the lower the boiling point and the higher the freezing point. So the higher the vapor pressure, the weaker the forces in that bond. All right, so I have 3 examples here, I think. What's the molal concentration of ethylene glycol? So that's a non-electrolyte. And like I said, we're only talking about non-electrolytes right now because if you're looking at an electrolyte's freezing point or boiling point depression, you have to take into account that that electrolyte is going to dissociate into its ions, and that's going to change the solution. So you have to take that into account. So we're looking at non-electrolytes, things that don't dissociate for now. So what's the molal concentration of ethylene glycol, which is a non-electrolyte solution whose freezing point is 2 degrees Celsius? Well, the freezing point depression formula says that the freezing point depression equals the molality of the solution times the Kf, the freezing point constant. So we're looking for the molality here. So if I manipulate the formula to get molality by itself, I get the freezing point depression divided by the freezing point depression constant equals the molality. So now I sub in my numbers. What's our freezing point depression? Well, freezing point depression is always a negative number. So this solution has a freezing point of negative 2 degrees Celsius. So it's important to flip that sign. Your freezing point depression constant is right here, negative 1.86 degrees Celsius per mole. So your molality ends up being 1.07 moles per kilogram. That's the units of molality. Now, if I didn't make that freezing point negative, if I didn't make that negative 2, and I left it positive, I would get a negative value for the molality, and that wouldn't make sense. So that's why you need to change that freezing point into a negative, because at freezing point depression, you're lowering it. So it's going to be a negative number. All right, calculate the boiling point and freezing point of a solution. Okay, so the freezing point and the boiling point of a solution prepared by mixing 102 grams of table sugar and 375 grams of water. And I give you lots of information here. So this is going to be interesting. I give you the boiling point constant for water, the freezing point constant for water, the boiling point of water, and the freezing point of water. So the first thing I'm going to do is calculate the molality of this solution. And the molality of the solution is the moles of solute, which in this case is this thing that's being dissolved. So that's the sugar. The moles of solute, sugar, over the kilograms of solvent. Solvent here is water. So I need to convert my grams of sugar into moles of sugar. So if I have 102 grams of sugar, 1 mole of sugar, I know, weighs 342 grams approximately. So grams cancel, and I get 0.29 moles of sugar. Now my solvent's the water, 375 grams. So you move the decimal place over twice. So that's 0.375 kilograms of water. You could also divide by 1,000. There's 1,000 grams in a kilogram. So that's another way of doing it if you need to see it. So the moles of solute, I have 0.29 moles of sugar over my kilograms of solvent, 0.375. And I get my molal concentration to be, I'm going to take it to 3 decimal places, 0.073 moles per kilogram. So I did this first because I'm going to need this to calculate the freezing point and the boiling point depression. And that's my molality. All right, so I will start with the freezing point of the solution. I'll make 2 sides here, one for the freezing point, one for the boiling point. So the freezing point depression formula says that the freezing point depression equals the molality of the solution times the freezing point depression constant. Looking for the freezing point of this solution, but notice that delta TF equals the initial freezing point depression of the solution minus the one that we are about to calculate. So you have 2 options here. You can make this KF for water negative, and that way you're going to get a negative value for your freezing point depression constant, or you can manipulate this formula in the end and move your final number over, and that would make it negative. So I'm going to opt to just change the KF of water to negative. So that's going to give me 0.773 molal for my molality. I'm going to make my freezing point depression constant negative because it's depression constant. And that's going to equal my freezing point depression. So this is just a little bit easier way. So the freezing point depression here, this solution will freeze at approximately negative 1.44 degrees Celsius. So if I opted to do it the way of using delta TF, I would have just subtracted 0 from positive 1.44, and that would have made it negative. Either way is fine. So now let's look at the boiling point of this solution. Boiling point elevation equals the boiling point constant times the molality. Either way, it's associative, so you can switch them around. So the boiling point of this solution, now here we have to take into account the boiling point depression, the change here. We have to take this into account because the boiling point of water is 100 degrees Celsius, not 0. So we can't just manipulate that around. So I'm going to do it the old-fashioned way here. I know that the kb of water is 0.52. I know that the molality of our solution is 0.773. So that means that this solution is going to have a final boiling point of 0.401. Now I'm going to add this to 100, which is the standard boiling point of water. So this solution will boil at 100.401 degrees Celsius. It's boiling point elevation. So I add this to the boiling point of water. So the boiling point of this solution, the boiling point elevation, is 100.41 degrees Celsius. Okay, this is a conceptual problem. Given the vapor pressures of the following non-electrolytes, determine the following. So we have ethane, pentane, isopropyl alcohol, and acetone, all non-electrolytes, so we can compare them accordingly. So the first thing it asks for is to order the compounds in increasing boiling point. So the compound with the highest boiling point is going to have the lowest vapor pressure. So the lowest vapor pressure here is isopropyl alcohol. So this will have the highest boiling point. So if I'm ordering them accordingly to that, the lowest boiling point would be ethane, which is number 1. Next would be pentane, number 2. Next would be acetone, number 4. And finally, the highest boiling point would be isopropyl alcohol, number 3. Also notice intermolecular force strength-wise, here you have a hydrogen bond, a pretty strong hydrogen bond. So that would make sense that it has the highest boiling point. Which compound has the strongest intermolecular forces? Well, I already hinted at that. Isopropyl alcohol has the strongest intermolecular forces. If you didn't recognize the hydrogen bonding, you could also tell that it has the strongest intermolecular forces because it has the lowest vapor pressure. So that would mean it has the strongest. So I'll put an S here for strongest. Now the weakest would be the one with the highest vapor pressure. In this case, ethane, C2H6. So I hope this helped you to understand boiling point depression and colligative properties of non-electrolytes. In my next video, we'll do more advanced calculations with colligative properties and those of electrolytes. Thanks for tuning in.